Hi, I'm Arindam. Today I'll be talking about our paper, Fast One-Class Classification using Class Boundary Preserving Random Projections. This work was published in KDD 2021. So why is the problem of one-class classification interesting? Many real-world applications lack easy access to counterexamples. For example, to detect credit card fraud, we have plenty of data for normal transactions, but it is hard to get much data about fraudulent transactions. And unlike binary classifiers, one-class classifiers can train using only normal class data to learn to detect abnormal behavior. Why are we proposing a new algorithm for the task when many solutions exist? Well, the applications we saw previously may need to deal with high-dimensional datasets, ranging from a few hundreds to tens of millions of features. And both training and test time of extant one-class classifiers scales poorly with dimension. OCSVM, a popular one-class classifier, takes 2.5 hours to train and 30 minutes to query on a dataset with 3 million features. DROC, a state-of-the-art deep one-class classifier, takes 5 hours to train and 1 hour to query on the same dataset. Frog takes 30 minutes to train and 25 minutes to query on the same dataset while performing better than both of them. Our main contributions of this paper are as follows. We present Frog as the solution to the scalability challenge. We show that Frog is stable and its bias reduces exponentially with the size of training set. And we empirically show that Frog performs well across a wide range of datasets with excellent scaling. Now let's see the key idea behind random projection-based one-class classifiers using an example. Given a set of data points from the normal class, we choose m random vectors. In this example, they are W1 and W2. We call these vectors classification directions. The choice of m provides control over the trade-off between performance and stability. Then we project our training points onto these classification directions, taking the extrema in each direction, A, D, E, F, we get a bounding box around our dataset. Let us see how this fares against some new test points. A previously unseen example from normal class, Y3, is now correctly classified as normal. An example of abnormal class, Y2, is also correctly classified as not normal. But an abnormal point, Y1, is now being incorrectly classified as normal. This is the problem of multiple modes in dataset. Our normal data points are clustered into two regions, but the region in between doesn't represent the normal data. This is a common problem faced by many extant one-class classifiers. Our solution is to simply split the box whenever the projected points are separated by a distance greater than epsilon. Now, Y1 is correctly classified as not normal. We now present some theoretical guarantees for Frog. First, some notations. A is a random classifier defined by the training set S and a random decision string R. AS denotes the classifier trained on a training set S. The error of AS on random point Z is defined as the expectation that the classifier output does not match the label of C. Risk is the expectation of the error over the distribution of the data. Since we do not know the distribution of the data, we define empirical risk, the average error on the set S itself. Now let us define the notion of uniform stability for randomized classification algorithm. A randomized classification algorithm A with 0-1 loss V is said to have 0-1 uniform classification stability beta, eta, if for any set S, if we remove 1 point from S, the error cannot change by more than beta with probability 1 minus eta. An algorithm is 0-1 uniform classification stable if beta is O of 1 by size of S, and eta is O of e power negative c times size of S. We show a result of general interest in our paper. A 0-1 uniform classification stable algorithm converges to zero bias at the rate exponential in size of S. Finally, some theoretical results for FROC. FROC with epsilon equal to 1 is 0-1 uniform classification stable with probability 1. And the empirical risk of FROC approaches real risk exponentially fast with the size of S. This means that given enough samples, if FROC does well with training data, it will do well in the real world. Now remember, the goal was to make scalable one-class classifier. So we do this in 3 ways. First, DROC. We use discretized projection, which gives us up to 10 times speed over FROC. SDFROC, using sparse projection vectors, which gives us 2 times speed up over DFROC. And finally, PARDFROC, parallelizing the computation of SDFROC, giving us another 2.5 times speed up over SDFROC. Let us see each of these steps in detail. First, DFROC. In continuous space, it takes big O of number of intervals to check membership of a point in an interval. In DFROC, we discretize the projection space into a certain number of bins controlled by gamma. Gamma decides the number of bins spanned by the epsilon. In this example, gamma is 2. That's why we split the boxes when the distance is delta 2, but not when the distance is delta 1. Note that as gamma tends to infinity, the intervals are same as that of continuous space. This gives us O of one way to check whether a point lies in an interval. And it also helps us parallelize the implementation later. DFROC gives us 2 to 10 times speed up over FROC. Now let's talk about SDFROC. The high-dimensional dataset which we are dealing with are often sparse. Using dense projection vectors make these projections dense and make further computation expensive. We therefore sample our projection vectors from Akliopta's distribution. This gives us sparse projection vectors with only S fraction of non-zero entries, potentially reducing the computation factor by 1 minus S. Using such vectors, we get up to 2 times speed up over DFROC. Finally, let's talk about PARDFROC, how we parallelize the computation of SDFROC. This figure shows the architecture of the parallel system. The computation takes place in 3 phases, each of which has a parallel phase in blue and an aggregation phase in purple. First, random vector generation phase. In the parallel step, for each batch, we generate sparse random vectors, generating only the necessary entries. In aggregation step, we create our final set of projection vectors by adding up the vectors from each batch. Akliopta's distribution ensures that we maintain the sparsity. Next comes the projection phase. In the parallel phase, we project all the batches onto the vectors generated in the previous phase. Then we need an aggregation phase to compute the scalars so that we can uniformly scale all the projections. Finally, the interval generation phase. In the parallel step, we generate a discrete interval vector for each batch. To aggregate all the interval vectors, we simply take a logical OR of the interval vectors for all the batches. Parallelization gives us up to 2.5 times speed up over SDFROC. Now for the experimental results. This table shows some of the data sets that we use to compare the algorithms. We see that the number of features range from 100 to 16 million, and the number of training samples range from a few hundred to 3 million. These are the baselines that we compare FROC against. They're divided into non-deep methods and deep methods. Non-deep methods are mostly SVM tree or random projection-based methods. And the deep methods are GAN's variational autoencoder or DROC. Now let's look at the Classification performance. Frog outperforms other baselines on area under the ROC curve on all but one datasets in which we rank 2 out of 8. In some datasets like malicious URLs, the gain is as high as 8 percentage points. More datasets and details are available in the paper. Here we show the computational speed of Frog. We see that Frog outperforms the methods in terms of speed. Note that isolation forest comes close in training time, but it suffers significantly during the test time. Also note that Kitsune data, which has just 115 features, isolation forest is faster than Frog, but clearly cannot scale well when the dimensions are large. Here we show how frogs and the baseline scale with dimensions. Notice that isolation forest is faster to train initially at low dimensions range, but frog outscales it when the dimensions increases. The scaling problem is more significant for test times for isolation forest. Here are some open problems based on our work. We want to look at Frog as a data-dependent kernel, which could serve as a replacement for kernels like RBF. We are also working towards adopting Frog for multi-label and hierarchical classification. Finally, we want to use the theoretical framework introduced in the paper to analyze other classification algorithms. Thank you.